Hi, everybody. Thank you for being here today for our third CosmoVerse training series session with Dr. Jurgen Mifsud. Thank you, Jürgen, for accepting our invitation today. CosmoVerse, as you may know, is a network of over 400 researchers in Europe and over 600 globally, with the aim of unifying efforts in confronting the question of cosmological tensions and understanding how different parts of physics can contribute to that effort. Dr. Mifsud is currently a postdoctoral researcher here at the Institute of Space Sciences and Astronomy at the University of Malta. He obtained his PhD from the University of Sheffield under Professor Carsten van der Bruck. He then went on to take on a postdoctoral position at the Korea Astronomy and Space Science Institute, KASI, where he worked on Planck CMB data and SKA forecasts. He has since taken on a postdoctoral position at the University of Malta, where he works on machine learning applications in cosmology. He has also mentored numerous PhD students and been involved in leadership activities in our institute. In this third training session, he will present to us the latest approaches to data-driven cosmology. Jürgen, please start in your own time. Thank you.
Thank you, Jackson, for the invitation, and thanks for the introduction. So, as Jackson mentioned, this session is about data-driven cosmology. I will be mentioning some techniques which are currently being used in cosmological data in order to analyze or infer results from cosmological data using machine learning techniques, which are definitely under development from several people in the community. So here I shared with you my GitHub page. All the material which I will be presenting will be available on this page. And I will go through the first set of techniques. However, before moving on to the techniques, I would like to start with a brief introduction. And in order to do so, I'd like to provide you with a brief timeline of neural networks, because I'm going to start off with neural networks, and then at the end you will see the application of a specific type of neural network as well in order to infer results from cosmological data. So we'll go through a brief timeline. We can start off with the 1940s, in which we've got Warren and Walter, who published a logical calculus of the ideas immanent in nervous activity. This laid the groundwork for artificial neural networks, since there was the proposal for a computational model of the brain. And then going into the late 50s, Frank introduced the perceptron, and as we will see, we're going to start off with this idea so that we start understanding how a neural network is developed. And in order to start off, we're going to start with a single layer neural network. It is known as a perceptron, and this has been shown at the time that is capable of binary classification. Definitely, it is an elementary application. However, with this application, we can immediately see how a single layer neural network works at the very fundamental level. And then during that time, we've got the first learning rule, let's say, the introduction of the delta rule, or the least mean squares algorithm, which is a simple method in order to train perceptrons. In the 60s, then the perceptron falls out of favor due to its limitations in solving nonlinear problems, as we will see. And this has been highlighted in the book by Marvin and Seymour, which is titled Perceptrons: Introduction to Computational Geometry. And we will see how geometrically perceptron fails to solve nonlinear problems. So there was then an interest in neural networks under the framework of different techniques, and definitely researchers then had to explore more complex architectures and learning algorithms. In the 70s and 80s, we have the backpropagation, which is a powerful algorithm for training multi-layer neural networks. So as you can see, we have moved now from one layer. You will see even visually now what we mean by a one layer or a multi-layer neural network. And researchers at the time started to explore the possibility of considering multi-layer neural networks. And these kind of networks have been primarily developed and also popularized by multiple researchers, including the people mentioned over here. And I should mention, especially in this lecture, which has been very well timed, although it's a coincidence, I would say, with the Nobel Prize. In the 1980s, 1982, John Hopfield was able to prove that a form of neural network, which is now called the Hopfield net, could learn and process information. And it also converges after enough time under any fixed condition, which is a very important criterion. This was a breakthrough, as it was previously thought that nonlinear networks would, in general, evolve chaotically. So that is why, well, one of the main reasons net is considered as a breakthrough in this field of research. And then late 1980s, we've got the introduction of convolutional neural networks, better known as CNNs. I'm pretty sure that you've heard about the CNNs in different applications, which is a specialized type of neural network architecture, which is mainly well suited for image processing tasks. Nowadays, this technique has also been adapted to cosmology and several astronomical data sets, especially when it comes to imagery data. In the 1990s, there is a specific period in which there was a reduction of interest and funding. It's also known as the AI winter, due to computational power. Okay, there was also a lack of large data sets. So sort of the need and the interest for neural networks was slightly lacking at the time. Then in 2006, Geoffrey Hinton, along with other colleagues, they proposed deep learning as a subfield of machine learning focused on learning representations of data through multiple layers of abstraction. So now we're moving on into another era, that is of deep learning. Then the deep learning community achieved a breakthrough using ImageNet large-scale visual recognition challenge. That is now the deep convolutional neural network. Okay, this has also been known as AlexNet. So as you can see, we have moved from one layer to a multi-layer, and now we're also seeing this kind of advancement in the convolutional neural networks as well. Then in 2014, we had GANs, which are the generative adversarial networks. These have been introduced at the time, which revolutionized the field regarding generative modeling in this case. So it's again a different technique which is still being used, especially in the generation of synthetic data, but synthetic data which is still realistic. Then in 2015, we have the LSTMs, which are long short-term memory networks, which is a type of recurrent neural network architecture designed for sequential data, which became widely adapted, especially in natural language processing. and other time series prediction tasks. And then, as you all know, we have the OpenAI release of GPT, which is the large-scale language model based on transformer architecture. As you can see, there is a wide range applications to neural networks. So apart from astronomy, cosmology, astrophysics, which are the main applications for our purposes, these techniques have also been adapted in other areas of research. And obviously, I have to mention at the start of this lecture the Nobel Prize, which was Nobel Prize in Physics of this year. This has been awarded for the foundational discoveries and inventions that enable machine learning with artificial neural network. This has been given actually this week to John Hopfield and Jeffrey Hinton. These have also been mentioned in my historical outline of neural network. So let's now move on to the birth of artificial intelligence. If we go back to the foundational level of artificial intelligence, we have to go back to Alan Turing in the 1950s and his paper called Computing Machinery and Intelligence. The first question that he asks in the paper is the following: can machines think? Okay, and this question is considered to be the birth of artificial intelligence and the beginning of the brief history of AI. And then, as you might have already heard, we've got the imitation game or the Turing test. Now, when it comes to artificial intelligence, for which we have John McCarthy as the father of AI, he specifies, so John specifies that it is the science and engineering of making intelligent machines. There has been a lot of interest over the years in AI. Definitely now, artificial intelligence is all around. And there was a particular conference which is related to a summer research project on artificial intelligence, which is quite well known. This took place in the 1950s, 1956, which began the field of artificial intelligence. Over there, scientists who participated in this conference, they brainstormed on AI, and this event led to the next generation of scientists to be inspired to work on such techniques. The main inspiration of neural networks, so going back to neural networks, is coming from the biological aspect. So over here, you can see like the representation of the neurons in our brain and how they function with one another. And basically, a neuron is so-called transmits a message via the firing of a neuron. And in fact, this is the terminology that we use in machine learning as well. So it's not only used in the biological field, but this is also used in our field of machine learning. And if we look again at the biological aspect, when we transmit a signal, so when we have to induce a particular message through the neuron, this is how it works. Okay, so there are specific obviously parts which are biological parts in which we can explain how a signal is transmitted from one neuron to another. And in fact, what happens is that we have a particular part of the neuron which is called the dendrite. The dendrites, which are basically these parts of the neuron, they receive the signals from other neurons because they are the attachment part of the neuron with other neurons. So once the neuron receives the signal via the dendrite, then the information is processed via the soma, this part, and then we've got the transmission of the signal via the axon. And then at the end, you've got the synapse, which is the point of connection to other neurons. So after the whole process, then you've got the transmission of the signal from one neuron to another. So we think about this from a computational point of view. Then what is happening here is that the neuron, it takes an input, which is the from the dendrite, it processes it like the CPU, which is the soma, and then you've got the cable-like structure, which is the axon. So all of these bits and pieces, they are all directly related to the computational aspect, so in terms of hardware. And although obviously we are simplifying the biology of how we transmit a signal from one neuron to another, and this might look also inaccurate, however, this is, let's say, at a high level what really goes on. Now we're going to move on to the most basic neuron, which is the Pitts neuron, which is simply a binary device. Okay, so in this case, we will just be referring to a 1 or 0 output, okay, just binary, just to introduce you to the neuron itself, so to how a neuron really works. So in this case, this kind of neuron, this had multiple inputs, but just one output. And what happens is that if the combined inputs exceed a certain threshold, we would say, as I have mentioned, from the biological perspective, the neuron would fire. Okay, so once you establish a certain threshold, if you exceed, so if the input signal exceeds that threshold, the neuron would fire. Otherwise, it would remain inactive. Okay, so otherwise, nothing will happen. And the simple yet powerful concept mimic the basic function of neurons in the brain. So you either pass the signal or you do not pass the signal. It has only two types of inputs, which are the excitatory part and the inhibitory part. In order to distinguish now mathematically, okay, between these two kind of inputs, we have to use weights. If the weights have a positive magnitude, then you're going to excite the neuron. If the weights are negative in magnitude, then you're going to inhibit the neuron. So in that case, you've got inhibitory weights. Now, the inputs for this neuron could either be at 0 or a 1. Those are the two kind of inputs. The threshold function is also known, as you will see in the upcoming techniques, it's also known as the activation function. Why? Because you're going to activate or deactivate the neuron. So the output signal, in this case, is denoted by Y out, is 1, because the output is either 0 or 1. So it's going to be 1, so that is the neuron will fire if the sum, that is the input, is greater than or equal to a given threshold value. So if we're going to exceed, so if the input is going to exceed the threshold, then the output will be 1. So the neuron will fire. If the input does not exceed the threshold, then the output will be 0. And this is the mathematical representation. So this first part, y sum, that is representing the activation function, which incorporates the weights and the input. So it's the product of the weights and the input. You have to sum up over all the inputs and over all the weights. And then the output depends on your threshold that you're going to set in your neuron. Okay, so y out is going to be 1 if x is greater or equal to 1, or else it's 0 when x is less than 1, if the threshold is set to 1. And this is the graphical representation of this kind of neuron. So as you can see over here, we have the input signals, which, as we have seen mathematically, the input signals, there can be multiple input signals. So you can have n in total with along their respective weights. So I have x1, x2, xn along with the respective weights w1, w2, wn. Then in the summation junction, we will be considering the summation of the product of the weights by the input signal. You will end up with the summation, and then you will apply the threshold function, through which you will determine the output of the neuron. So that is the mathematical and graphical representation. Now, how can we implement this in one of the packages which is mainly used for machine learning, which is TensorFlow in Python? So we're going to be using TensorFlow. Now, you might say this is too much for such a simple neuron. However, you will get into the idea on how we're going to use this package in order to adapt this very basic and elementary type of neuron. So what we'll be doing is that what we need to compute are mainly two things, okay? So the first one is that in this function definition here of the neuron, we're going to consider the inputs. We have the weights, because with the corresponding inputs, we're going to have the respective weights and also the specified threshold value. Okay, so in that case, that will be part of your input argument of your function. Then, once you provide the inputs, the weights, and also the specification of the threshold value, then you can compute the weighted sum. The weighted sum is simply the multiplication of the inputs by the weights, and you apply the reduced sum from the TensorFlow package, and then you can compute the output. In order to compute the output, this is the activation function, in which if the weighted sum is greater than or equal to the specified threshold, then the output will be 1, otherwise it will be 0. So here we're testing, in the case of an input signal of 1, 1, 0, and the weights are -0.2, -0.2, and 0.6. So you define the inputs, you define the weights, again, in terms of TensorFlow, as a constant in both cases. And then you have to specify the activation function. The activation function has to be specified again as a constant within TensorFlow. Once you specify all the inputs, then you can move on to the output, and we can call the neuron function. In this case, the output will be 0. Now, you can apply this to any other Boolean combination. And in fact, this is the second part of this lecture, in which we're going to apply this technique, this very basic neuron, to other Boolean combinations. We can now move on to the perceptron. So up to now, we have an idea on how a single neuron with multiple inputs provides us with an output. In the case of the perceptron, this is a probabilistic model for information storage and organization in the brain. That has been the let's say the introduction to the perceptron at the time when it was introduced, and it is considered as the oldest and most simple of the ANN algorithms. In the case of the perceptron, we should have a look at the linear boundary, and we will see what we mean by a linear boundary in the following graphical representations. In this case, the perceptron will work by learning the weights of the input and then use them to make predictions. So we're going to consider the weights of our input. The weights will be changed in process, and then once we have the final weights, we can make the prediction from the neural network algorithm. The weights which are learned through this process, this part of the process is called the training of the neural network. So the neural network will be learning new weights. By learning new weights, this means that we are training our perceptron. We are training our neural network. And the model is presented with a series of input-output pairs. And in process, you have adjustment of weights. The weights will be updated according to the error, which will be determined by calculating the predicted output with respect to the true output. We will see this in the upcoming examples. So if we consider over here the linear boundary that I was referring to, and we consider the AND logical operator. So with regards to the table, we can have definitely either a 0 or a 1 as an input. So in the case of a 0, 0, we get an output of 0. 0, 1, we get 0. 1, 0, we get 0. 1, 1, we get 1. We can represent this table graphically in this figure. And what we're going to do here is that we're going to check whether we can make use of a linear boundary, so a line, basically, in order to separate the 0 output from the output of unity. So in the case of an AND, as you can see, we have 0, 0, 0, 1, and 1, 0 as input. They will give us a 0, and these are denoted by black filled circles. In the case of an input of 1, 1, we get an output of 1. So in this case, the output is different. Okay, and this is denoted by this open circle. Now, if we were to draw a line in order to separate the black circles from the open circle, in this case, it is possible, and we say that the AND logical operator is linearly separable. So we can separate the two from each other. This also applies if we apply the same technique for the OR operator. Because in the case of the OR, basically, it is the inverse, as you can see, because in the case of a 1, 0, 1, 1, 0, 1, in these cases, we have open circles. Why? Because in this case, the output is 1. And in the case of a 0, 0, which is the only case, we will get a filled circle. Okay, reason being is that we get at 0 when we input at 0, 0. And as you can see, we can also separate the open circles from the filled circle. So again, we can draw a line. So we can say that in this case, it is also linearly separable. Now, moving on to the XOR, if we move to the XOR, we will have a different output. In a sense that in the case of 0, 0, and 1, 1, we will get a 0. In the case of a 0, 1, or 1, 0, we will get a 1. And if we try to linearly separate the two from each other, so that is the outputs, this will not be possible. Okay? It will not be possible to separate the black circles from the open circles by just using one line. So we can say that the XOR is not linearly separable. And moving on now to the mathematical formulation, because that was the graphical interpretation. So we can view the perceptron as representing a hyperplane decision surface in the n-dimensional space of instances. And this is what we are actually doing. We are finding a hyperplane in the manifold which will separate the two from each other. And the perceptron will output a 1 for those instances lying on one side of the hyperplane, and it will output a 0 for those which will be on the other side. So mathematically, the decision hyperplane, so the line that we're seeing basically, can be represented by a dot product of the weights with the input. Okay, so we have w dot x is equal to 0. Now, some sets of positive and negative examples cannot be separated by any hyperplane, and as we have seen, those that can be separated, those are known as linearly separable sets. And in the case of a single perceptron, this can only be used to implement linearly separable functions. It cannot be used for non-linearly separable functions. And as we know from this example, it will take, so the perceptron, it will take both the real and the Boolean inputs, along with the associated set of weights and the bias. There will be a bias involved when we consider the perceptron. In process, we'll be learning the weights, and we get the output as a function. So this is graphically what is happening. So we've got the input signals, which are, again, multiple input signals. And we have here the linear combiner. So in the first case here, we can see x naught, w naught. So x naught is the input, w naught is its associated weight. This part here is known as the bias. And then for the other inputs, so x1, w1, x2, w2, those are, let's say, the standard inputs. We combine all the inputs, including the bias, and then we process it through a very similar procedure as before. Now, perceptrons, they can represent all of the primitive Boolean functions, which are the AND, OR, NAND, and NOR. As we have seen graphically, we cannot represent the XOR function, okay? Because the XOR is not linearly separable. Now, let's see how we can apply, even by hand, the perceptron train rule. Now, one way in order for us to learn the new weights, okay, is to iteratively apply the perceptron to each training example. So, which means that at each iteration, we're going to update the weights. And then in process, we'll be modifying the perceptron weights until we reach convergence. So this process is a repetitive process. It's an iterative process, which has to be done as many times as needed until you end up with a full classification of the training. Now, the weights are modified at each step according to the perceptron training rule, which will revise the weights Wi along with their associated input Xi. So what will happen is that your initial weight Wi will be changed, will be updated to your new weight Wi plus delta Wi. Now, the delta Wi is the change in weight. The change in weight is dependent on the difference between the target and the output, which are denoted by T and O. So T is the target output of your training example, and O is the output generated by the perceptron at that level of training. It's also dependent on eta. Eta, it's a positive constant, which is known to be as learning rate. And then definitely Xi is the associated input. That is the change in weight that we're going to have iteratively from one step to another. Now, the role of this learning rate is to moderate the degree to which the weights are changed. It usually is set to a small value, like 0.1. However, this depends on the application at hand. And the nice thing about this procedure is that one can prove that with a finite number of applications of the perceptron, this converges. Okay, so basically what happens is that the weight vector is able to correctly classify the training examples, given that they are linearly separable and sufficiently small eta is used. This has been reported in a paper in 1969. If the data is not linearly separable, then convergence is not assured. And definitely what we're doing here, so we'll look at this graphically. What we're doing is that we are kind of using the gradient descent method, okay, when we're trying to minimize the error of a particular problem at hand, so like having a likelihood function or a chi-square function. And this is precisely what we are doing. We are changing the weights until, so during the learning process, during the training process, during the training phase, we are learning, so the neural network is learning about the problem at hand, and this is similar to minimizing, let's say, the error of hypersurface of your likelihood or your chi-squared function. And as you can see, for example, here, once we minimize the error, then at that point at which we have the minimum and we reach the minimum, we have the best fit line, for instance, in this case, of regression. This is just in order for you to make a link to those areas which are maybe more familiar to you. And as you know, in other applications, so which are the standard statistical applications, we also always talk about what is known as the goodness of fit. Now, in this case, these algorithms, they don't have access to such goodness of fit, but we have what is known as a loss function. The loss function translates to a similar idea of goodness of fit. If we consider regression, we can consider residuals. If the residuals are large, definitely the fit is not good at all. So what we try to do is we try to minimize the residuals in order to get a better fit. And here you can see, for instance, we're fixing the y-intercept of this line, and we are changing the slope of the line. Okay, so definitely the residuals will change. And here you have an application of a perceptron using the XOR and OR logical operators, using simple Python programming in order to implement them. So in order to implement, let's start off with the OR. In order to implement the OR, it simply returns a Boolean. Okay, so we're going to input x1 and x2 in this case, and the return will be dependent on the Boolean value of x1 or the Boolean value of x2. And when we input, then obviously you have to specify. So x in this case is an array of 0, 0, 0, 1, 1, 0, 1, 1. And this exhaustively covers the space of two inputs, because we have 0 or 1. And those are all the permutations that one should consider in the input. And then in order to apply the OR function, you have to do is you simply apply this function of OR to all these inputs. And this is done in this line of code. Now, similar to the OR, we also have the XOR. In this case, definitely the return will be in line with the XOR logical operator. That is, when the Boolean of x1 is not the same as the Boolean of x2, then you will get your output as a 0 or a 1, depending on x1 and x2. Similarly, over here you have the AND. Instead of the OR, here is a logical operator, we have AND in between. So now in our Python script, we have the logical operators, which are XOR, OR, and also the AND logical operator. Now, we're going to consider the decision boundary, which I've already mentioned when we're looking at these examples graphically. And definitely, when we open up this decision boundary equation, you will end up with a hyperplane equation, right? So where you can see at least even for two inputs, okay? Because remember, with two inputs, x1 and x2, you also have the input of bias, which is denoted by W naught. Okay, the weight of the bias is W naught. So I have W naught x naught plus W1 x1 plus W2 x2, that is equal to 0. In which case, that is representing a hyperplane in our problem, and we are going to find a solution to that. So in order to represent all of these cases, we have seen, so this code here is simply visualizing all the graphics which we have introduced before, in which, in the case of the OR, it is linearly separable. We can draw the boundary in order to separate the ones from the zeros. In the case of the AND, we can also do that because we can separate the ones from the zeros. With regards to the XOR, this is impossible because the problem is non-linearly separable. So you cannot separate the ones from the zeros by simply considering a line. Now, in order to make use of this script, if we consider a true, which is 1, a false, which is 0 in our case, and in this case, we have to create the logical OR operation. The logical OR operation, one can create it quite easily, in which the input is again similar to the input which we have seen before. So we have all the combinations here, the 4 combinations, and then the corresponding output of these 4 combinations of our Booleans. And then we return the output. We similarly apply this for the AND, and we also do this for the NOR and XOR. Okay, so we have all these logical operators, and now we can move on to the definition of the perceptron class. Now, in the case of the perceptron class, we have more input variables. Reason being is that when we calculate the iterative weight, so the new weight, we have to specify a learning rate, and we have to specify also the bias. Okay, so in this case, we should specify those variables which are required in order for us to iteratively compute the next step in the perceptron. So in this case, what's happening is that we are setting the learning rate to 0.8, the number of epochs, which is the number of iterations, to 10. We're specifying the input weights, -1 and -1, and the bias value is 1. The weight of the bias, it's -1. We are then setting the learning rate, epochs, input weight, value of the bias, and the weight of the bias. All of them, those are set inside this class called myPerceptron. Now, we're going to specify the step activation function. Now, there are different activation functions, as we will see shortly, but stick to the most simplistic activation function. We can consider the step activation function, for which if the threshold is greater or equal to 0, then the output is 1. If the activation, so the value, is not greater or equal to 0, then the output is 0. So basically, the neuron will not fire. Okay? And now we can move on to the actual procedure. So what's happening in this case is that we're going to consider the first epoch. We're going into a for loop. And in this for loop, we're going to train the model. Okay, as we have seen, this is the training phase. This is the phase in which our neural network will be trained on the problem at hand, in which, in our case, we are just considering logical operators. So we're going to loop one epoch after the other until we can see stability. Okay, and that means convergence for our purposes. So we're going to consider at each epoch, we're going to consider the step activation function. Okay, once we compute the step activation function, and we apply the step activation function to that mathematical formulation which I have already mentioned. That is, we apply the activation function on the dot product of the weights with the input, okay, which we denoted by xi wi, plus the bias times its weight. And that gives us the total summation of the dot product, the total summation of our input, which will be considered in the activation function, and then the activation function, which we have set to the step activation function, will give us either a 1 or a 0. Then we have to compute the loss function. Again, in the loss function, you have to specify the type of loss function, for which case we're going to consider the mean absolute error. Okay, the mean absolute error is the most simplistic. Again, it is simply the difference between the predicted and the actual, that is the true value of your output. And that is computed over here, where I have yi minus y prediction. Y prediction is coming from the activation function itself. That is its output. Once we have the loss function, then we can move on to the iterative update of the weights. And that is using the optimization algorithm. That is basically updating our previous weights, which are here, and then we add to it our delta Wi, which is the difference in weight, depending on the learning rate, depending on the loss function, and the input xi. So now we have updated the weights. We will be updating the bias weight as well, because in this algorithm here, we have separated the weight of our input from the bias weight, that is the weight of the bias, in a similar manner, basically, because I have the bias weight plus the learning rate times the error, that is the loss function, times the bias, the original bias. So we have now at this stage updated our weights for our inputs and the bias. So we have our delta Wi, we have our new weights Wi, therefore we can compute our new prediction. And in this case, we have iteratively computed the next step. We do this for several epochs. In this case, we have specified 10 epochs. And we will then determine whether there will be convergence or not. Over here, we're keeping it simplistic in order for us to understand the procedure of how a perceptron works. So let's apply it to an OR logical operator. If we apply it to an OR logical operator, first of all, we're going to get X and Y, which are going to be X is going to be our input of our perceptron, and Y is going to be the true values of our perceptron. In which case, over here, we're going to have 0, 0 gives us a 0, 0, 1, it's a 1, 1, 0, it's a 1, 1, 1, it's a 1. That is a simple OR logical operator. Then we apply those inputs and outputs to the perceptron. So the perceptron is specified to work with a learning rate of 0.8, 10 epochs, input weights of -1 and -1, the bias value is 1, and the weight of the bias is -1. And here you have the actual output when we apply the perceptron technique to the OR logical operator. As you can see over here, you have the output of the predicted value of Y along with the error using the absolute error. The new weights, the new weight of each predicted Y along with the bias weight, right? So in the case of epoch 1, you can see that the errors here are not 0. So which means that there is a difference between the true output and the output which has been predicted by the neural network. In this case, the perceptron. So we move on to the second epoch, and you can see that we are changing the weights along with the bias weight, and the errors are still non-zero. We have -1, 1, 0, 0. In the third epoch, we still have non-zero error. There is a difference between the true value and the predicted value. So we've got -1, 0, 1, and 0. Again, therefore, whenever you have a non-zero error, you have to update the weights. And in fact, this is what's happening. And in the fourth epoch, similarly, we have non-zero errors. So we have to update the weights of the first predicted value, because it's 1 instead of 0. But then as you can see, at epoch 5, the errors are all 0. Why? Because the predicted value during the training, so the predictions that we got from the perceptron, they agree fully with the value of the input, which in this case is simply 0, 1, 1, 1, because that is the output that we are expecting from an OR logical operator. And as you can see, if we move on to the 6th, 7th, 8th, and so on epochs, there will not be any updates. Reason being is that in the mathematical formulation, we have an update on the iterative weights only if the errors are non-zero. If the errors are zero, then that isn't going to be an update. And therefore, we ended up with the training phase of our perceptron. So we can say that after 5 epochs, this perceptron learned the OR logical operator. So it knows exactly the weights that it should use. As you can see, the weights have changed from the input weights of -1 and -1 to 0.6, 0.6, and -0.2 for the bias. So the update of the weights has been done, and correspondingly, the training phase of this neuron has been concluded. Now, the graphical solution of what we have inferred, we can also represent the linear boundary that we have inferred from the training phase of our perceptron. In fact, by considering the boundary equation coefficients, we can infer the gradient and the y-intercept of our linear boundary by considering the ratios of W1 with respect to W2, so the weights of the input 1 with respect to input 2, and B, which is the y-intercept of the linear boundary, is again the ratio of the weight of the bias with respect to the weight of your X2, that is the second input. And this is the graphical representation of the inferred result. So as you can see, this red line over here, that is the linear boundary, which nicely separates the zeros from the ones. And as you can see, the job has been done properly by the perceptron training phase, because the graphical representation, again, is, as expected, separating our phase space from 0 to 1. And then an application of this, which we'll discuss in the second part of this lecture, is to apply this technique to an end logical operator. Now, we can also apply this in PyTorch. Okay, so we can apply this technique in PyTorch, definitely. So in this case, we're going to consider the perceptron class, which is part of this module, part of this neural network module within Torch, within PyTorch. And we're going to consider the linear part. So there's the linear equation function, and we've got the sigmoid forward propagation. Okay, so for the forward method, it means that we're going to forward pass of the model. We're going to use the sigmoid activation function so that we can map the output of the linear layer to a probability between 0 and 1. So in this case, it's going to be the sigmoid and not the step. Now we'll define the training loop for the perceptron. In the training loop, we will be iterating over a series of the input-output pairs, and then we use this iterative technique to update the weights of the model. For which we're going to use the stochastic gradient descent optimizer, SGD optimizer, in order to update the weights of our model. We're also going to be using what is known as the cross entropy loss function in order to measure the error between the predicted and the true output. Okay, this is different, slightly different than what we have been using so far. Again, this is within the package itself. Now, the loss function will be used to calculate the gradient of the loss with respect to the model's weight, which will then be used to update the weights using the optimizer, as we have already seen in the perceptor. So in this case, we will have the optimizer, which is the SGD. The criteria will be given with the loss function, and we're going to loop over the number of epochs. The application is very similar to what has been done in the previous case, in which we're going to consider the output as our model depending on the inputs. Okay, similar again, so to the trained inputs will be with all the variables which are necessary for the definition of the perceptron, and then we have the criteria. Okay, the criteria in order to select whether we're going to getting a 0 or a 1, that is the loss. Okay, and that is why the criteria here is equal to the loss variable. And then we're going to iterate, okay, epoch by epoch. We can also consider the accuracy of the model, a very simple estimator in order to compute the accuracy is the ratio of the correct predictions with respect to the total number of the test samples. It's simply a basic ratio on how many iterations you are considering with respect to the correct ones. And in this case, for instance, as you can see, the program here is much more compactified since we are using already built techniques. We're just applying them and adapting them to our needs. So as an input, we're defining a tensor within PyTorch with, again, the 4 combinations of the input, and the output is simply the OR gate. Okay, it's simply the OR logical operator. We're going to create an instance of the perceptron, and then we're going to train the model. And so we apply the training with 50 epochs, a learning rate of 0.8. In this case, we're also going to compute the accuracy. As you can see, the accuracy is 1. We have already seen that such a perceptron converges after 5 epochs. So after 50 epochs, this will have converged definitely. And in this case, we are using different loss functions with respect to the previous one. Now, going back to the activation functions, we have different activation functions. So here you can have a look at the different activation functions. We have like the sigmoid, hyperbolic tangent, ReLU, the identity, and the softmax activation function. These activation functions will be chosen according to the problem at hand. Now, most of the time, we test different activation functions, and then we will see which activation function would be the best, would give us the best performance for our problem at hand. So now let's apply what we have covered so far to the Sloan Digital Sky Survey, data release 14, astronomical objects. And we're going to apply the perceptron to this data set in order for us to separate the data set according to the class of the astronomical objects. So the data set that we'll be considering is a CSV file in which, as you can see, you are given the right ascension, the declination of the astronomical object, along with the redshift and the class of the object, so star or a galaxy. Now, if we were to plot, so we were to visualize the data points according to their classes, so we have star, galaxy, or quasar. In this declination right ascension plot, we have such an illustration of our data point. Now, if we were to consider these three types of classes, but now as a function of the redshift, so redshift as a function of the right ascension, you can see that there is a better, let's say, grouping between the three classifications. And similarly, if we were to consider the redshift against the declination of several of these three different classes of objects. Now, what we would like to do in this case is that we consider a subset, which is a clean subset from our data set, in order to separate the two data sets from each other. And here we consider, for instance, these two subsets in the redshift right ascension axis, and we're going to determine a linearly separable hyperplane here between the two. So what we're doing is that we are applying the perceptron technique in order to separate, or in order to classify, two different classes of objects. So we apply the perceptron. I'm going through it quickly because it's basically the same thing that we applied before. And we're going to consider initially a learning rate of 0.01, threshold of 0, and 10 epochs in this case. We're going to consider those data points which I have shown in the illustration, and we iterate over the optimization algorithm of the perceptron. We update our weights, and by doing so, we will end up with this line, which is, as you can see, separating the two classes from each other. So as you can see, this very basic elementary technique can also be used in order to separate two classes of data sets from each other. Okay, and then as a second example, then I would show you in the second part how to separate in the other phase space. So now let's move on to the second part of this lecture, that is the more applications, that is, of machine learning techniques. Okay, so another technique which I'm pretty sure that you've heard about is Gaussian processes. And this is Gaussian process regression. Gaussian process regression is what is known as a non-parametric approach in order to reconstruct observational data. So you are given observational data, let's say as a function of redshift, and we would like to reconstruct, meaning that we're going to fit our data set, obviously with uncertainties. And the idea is also to be able to make a forecast from our reconstruction, and also apply imputation techniques automatically, which will be coming from the reconstruction itself when we have gaps in our data. So the mathematical formulation coming from statistics, it's simply it's known as, first of all, it's known as supervised learning. It's a type of supervised learning technique, and when we apply it to stochastic data, we end up with a covariance matrix, and this comes from a statistical point of view. So in general, what we'll end up with is with a mean function mu of z. Let's consider the data is a function of redshift, and then we also get the 2-point covariant function. In this case, it's denoted by c z z tilde, okay, which is referring to the 2-point covariant function. So the realization, first of all, it's a continuization. It is a continuous function, okay, that we end up with, continuous reconstruction. And also, we can determine from this reconstruction technique the uncertainty. which is delta psi in our reconstruction or realization. So we end up not with a realization region, which is given by psi of z plus or minus delta psi of z. And it should be noted that we have mentioned that it is non-parametric. However, for such a technique, we should specify what is known as the kernel function. Okay, the kernel function is necessary in this reconstruction technique. And for instance, over here, you have the squared exponential kernel function, and is defined in terms of what are known as the kernel hyperparameters. The kernel hyperparameters are sigma f and lf, which in this case, these are the parameters of the kernel, but they are not parameterizing the function that we are reconstructing. And this is the distinction that we have between a model-dependent reconstruction and, in this case, a model-independent reconstruction, because the parameters, in which case they are called hyperparameters, they are not referring to the realization itself, but they are referring to the kernel hyperparameters. Now, what we will be doing in this technique is that first of all, the hyperparameters will be referring to a specific characteristic of our data. And in fact, sigma f is related to the variance. That is why sigma in relation to the standard deviation. And then the length scale, that is left. Okay? So that is the over the x-axis. In this case, the z-axis, that is a redshift space. And what we'll be doing is that the hyperparameters will be tuned in process in order to have a smooth realization of our data. So basically, the signal-to-noise ratio will be affected by this technique via the smoothing technique, which comes hand in hand with Gaussian process regression. Now, within PyTorch, there is a package which is gPyTorch. gPyTorch is a Gaussian process library which implements PyTorch techniques specifically written for the application of Gaussian processes. And what I will show you in this notebook is the application of such a technique to the JLA dataset, which is a supernova dataset. It is an old dataset. And then I will also show you its application to the most recent Pantheon Plus dataset. First of all, you have to set up the model. Okay, in order to use gPyTorch, you have to specify the GP model, which handles most of the inference. You have to specify the likelihood and the GP regression, the mean that you're going to use, the kernel, as we have seen, and also the multivariate normal distribution, which is the object used to represent the multivariate normal distributions within your realization. Now, in order to train the model, we make use of the PyTorch optimizers. That is why this is linked. So the training of the model will be considering the zeroing of all the parameter gradients. And then we will call the model, we compute the loss function, we call backward on the loss, we fill in the gradients, and then we take a step on the optimizer. Okay, so if we consider one of the kernels, okay, which is the third kernel, in this case, this is how we're going to call the Gaussian process from gPyTorch. And in such case, we're going to initialize depending on the training of X, the training of Y, and the likelihood. So then we're going to apply the forward method. So we have the data on X. We end up with a multivariate normal with the prior mean along with the covariance. So we'll end up with a vector mu of X and then the matrix representation of the error. Okay, so that is the mean and the covariance matrix of the Gaussian process, which will give us also the errors or the uncertainty in our realization. So we'll first initialize, as I have mentioned. So once we initialize the Gaussian process likelihood and the model, so this is the likelihood. So we're going to specify it's a Gaussian likelihood. We're going to specify the Gaussian process model. So we have the model over here. And then we're going to train the model. Now, when we say train, in this case, we're going to find the optimal model hyperparameters. Okay, we're going to optimize them in order to have a smooth realization of our reconstruction. Now, in this case, we're going to use the Adam optimizer. Okay, in this example, so again, as I've said, since we are within PyTorch, we're going to make use of all the functionalities that we have in PyTorch, in which case, for instance, we're simply going to make use of the Adam optimizer. And also, similar to the optimizer, we're going to choose a loss function for Gaussian processes, in which case we're going to consider the marginal log likelihood, again, within GPyTorch. We're going to consider 200 iterations in this case, going through the iterations. What we're going to do is that we're going to call the model. From the model, we're going to train it. We're going to get the loss and the backpropagation gradients. We're going to output those so that we know what the algorithm is actually computing. And then we're going to update our optimizer. At the end, we're going to evaluate the model. We're going to evaluate the likelihood. And then we get the outputs basically of your realization with the uncertainty along with the choice of your x-axis. Okay, so the choice of your redshift in this case. So in such a case, this is the realization that we end up with. So as you can see, these are the data points. Now, because there are quite few data points, I haven't considered the actual error bars just to depict where the mean of the data points is actually located, along with the realization with also the uncertainty that we infer from the Gaussian process regression. If we change the kernel, basically you have to repeat the same technique, so the same code. As you can see here, we have the output, so we have the iterations, 200 iterations, and we have the output of the loss function. So you can see the loss function, iteration by iteration, normally decreases, and therefore we are reaching a certain plateau in our loss function, and this is the output from the Gaussian process using a different kernel. As you can see, the difference you get from one kernel to another is not that significant, at least on cosmological data. I cannot say that this is a generic statement. However, when you apply different kernels, the end result will be similar. Not saying it's identical. However, that is the again another consistency check that you should carry out when conducting this reconstruction technique. So for now, I'm going to skip the application of Pantheon Plus. We'll get back to that afterwards. And I'm going to move on to the another application, which is decision trees. So the application of decision trees when it comes to the validation splits in our data.
Yeah, I try to look at the other.
Again, in this case, we're going to use the k-fold library, okay, which is again inbuilt. We're going to split our data set that is basically into the testing and training subsets of our data. This is something which you can do via this technique, via what is known as n-fold splitting, or else k-fold in this case. Once you specify the splits, then you will end up with what are known as the cross-validation techniques. I will just show you an application. I don't have the time to get into the actual technique itself. However, this is within a package sklearn. So at least you also know about another package. That is the k-fold. There's the k-fold library, let's say, within the sklearn package. In this case, what we're going to do is that we're going to consider a data set having different target colors in this case versus redshift, okay? And we're going to split, this is again the SDSS, but this is within the galaxy colors. So we're going to consider the colors of the galaxies, which is again another data set. And after the cross-validation technique, we should expect, if all the data points are in line with our training phase, so that is, if we manage to apply a machine learning technique and all our outputs are identical to the target, then all the data points should fit in a straight line. Okay? In this case, you can see some, let's say, residuals, but the majority of our points lie along this line, which is at an angle of 45 degrees. So that is y equals x, meaning that your target value is the same as the predicted value. If that is the case, so if the target value is the same as the predicted, then definitely all the values will be on the same straight line. However, in some cases, the training is not, let's say, robust enough in order to predict the same value as the target. And in that case, we can see that we can assess what is known as the accuracy. And this is where the k-fold cross-validation is important. Okay, so we can get an indication on our accuracy by using the k-fold cross-validation technique. And as you can see here, we can visually, even by eye, you can see that there are some outliers or residuals from our machine learning technique. And the last thing that I'd like to mention is referring to the application of artificial neural networks in order to infer model parameter constraints. As we have seen, artificial neural networks, so via the perceptron idea and so on, so via those basic fundamental ideas of neural networks, now we're moving on to a more sophisticated setup of artificial neural networks. So if we move on to a more sophisticated, that is, you consider a multi-layer, so you don't simply consider one layer of neural networks, but you have multiple layers, and I will show you what that means in a minute. Or, for example, you consider multiple neurons, so you have a number of neurons in order for your neural network to be able to learn all the parameter space of your parameters. As we have seen, the ANNs, so artificial neural networks, these are non-parametric techniques in a sense that they do not contain any information, or they are not interested in any information with respect to the cosmological parameters. And this is a big difference with likelihood functions, okay? In fact, when we infer model parameter constraints using artificial neural networks or machine learning in general, we refer to these techniques as likelihood-free techniques, okay? The reason being is that you don't require a likelihood in order for you to infer the constraints. And this idea has been extended to cosmological analyses, first of all, due to their nowadays easy application of the packages that are already available and you can implement in your cosmological analyses, and also the computing power which is available nowadays, especially on GPUs, because these techniques can also be implemented on GPUs instead of CPUs, making your process much faster. There have been a number of scenarios in which ANNs have been used in cosmology. For instance, Bayesian inference for calculating the power spectrum of the CMB and also the matter power spectrum. In the past, obviously, there has been a particular code which has been used in order to analyze CMB data using blind accelerated multimodal Bayesian inference, which is basically a combination of nested sampling and ANNs. There was this transition towards the implementation of ANNs in cosmological analyses. And recently, ANNs have also been used for the reconstruction. Reconstruction techniques similar to what we have seen in the reconstruction using Gaussian processes. You can mimic the same reconstructions and realizations using artificial neural networks, which I would say they are more conservative in a sense that when you compare the reconstructions that you get from a Gaussian process with respect to an artificial neural network, a Gaussian process normally over constrains your uncertainties due to its nature, whether ANNs are more conservative, meaning that they will be more lenient with respect to the uncertainties and their computation. So this technique has also been used in the reconstructions and also the reconstruction of modified gravity, such as, for example, scalar tensor theories. When it comes to artificial neural networks, they have also been used and are being developed in order to mimic the iterative process of NMCMC. You all know NMCMC analysis is quite, let's say, the standard practice that we have in our cosmology group that is basically related to the parameter inference technique. However, one can mimic this technique using ANN architectures, and this is one of the architectures that one can consider, where we have the input layers over here. Then we have a number of hidden layers. So that is basically the input layers are normally with respect to redshift dependent data. And then you have a number of hidden layers in which you have the processing of your training. And then you have at the end your output layer, which are then definitely the output observables, which you're going to compare with your data. So that is the output layer. Then over here, we have a multi-layer. Okay, so you have different data sets as well. Okay, so you've got different data sets and data sets in total, and then you're going to combine everything into one combined neural network, for which you end up with the same observables as an output. And this is one of the codes. It's called Confi, which is also publicly available. So what happens here in this flow chart is that you've got the cosmological model. You're going to simulate your data, so according to your observational errors. Okay, so this is your cosmological model here, for which you've got the target values. However, you will start off with the ANN model. Okay, so from the ANN model, you will be feeding in your synthetic data using ANN, after which you will be comparing with your training set with the observational data. Then you compare with your cosmological model, and this is an iterative process until you end up with your ANN model. Once you end up with the ANN model, then you can process or estimate the cosmological parameters. In this case, once we end up with a well-trained ANN, we can use the observational data as our target values. We end up with a ANN chain, not an MCMC chain in this case, and we get the derived cosmological parameters. So what we're doing is similar to MCMC. You have your data space from which we get to the parameter space, and this is comparison triangle plot, particular triangle plot as reported in the original paper of this particular code. As you can see, there is, so this is with Planck data. You can see a very good agreement between the neural network technique and the MCMC technique. Okay, over here they are denoted by blue and red. So this is a clear indication that one can mimic the MCMC technique with the corresponding ANN technique, which is appreciably much more faster when it comes to computational time, and when it comes to its complexity. It's let's say similar complexity to an MCMC, because the cosmological framework will remain the same. The only framework which you are changing is the sampling technique. One of them is MCMC, the other one is the neural network technique. So that is all I have to cover in the first part. Jackson, I'm not sure if we can go to some questions.
Thank you. Thank you, Jürgen. That was very interesting, and I'm pretty sure that has sparked a lot of questions in the audience. Maybe, yes, I agree. Maybe we could have some questions. Go ahead.
Actually, I would have a quick question too. That is exactly about your last sentences on how much faster these methods are compared to an MCMC analysis, for example. And if the amount of data also influences in how fast the computational time is or not.
Okay, so thank you for your question. Yes, I mean, I would say that it depends on your data set. So first of all, if you increase the number of parameters similar to an MCMC, then that will definitely affect the computational time. Also the volume of data that you're going to consider. But normally, in our case, for cosmological data sets, the number of data points is let's say, not a huge amount. However, when it comes to the comparison of speed, again, there isn't, let's say, one figure which we can quote. However, when we consider, for instance, we have seen like 5 times improvement, 10 times improvement, depending on the data set. For instance, if we just consider background level data sets, so such as, for example, cosmic chronometers, VAO data, supernovae data, for instance, over there, we have seen quite a significant improvement, even though the MCMC technique is fast at that level. When it comes to CMB data, it also depends on the cosmological model, because then it's the cosmological solver as well. However, there has been improvement. It depends. It depends on the model. It depends on the data that you are considering.
Okay, thank you. Thank you very much. Also for the talk. It was really interesting, and I think now it's much, at least for me, much more clear how we can use this kind of tools to to do cosmology.
If there are other questions, feel free to unmute.
Think about improvements from MCMC using neural networks. Are we strictly talking about computational expenses, or are there any benefits to using neural networks as opposed to MCMC in our analysis?
Yes, I mean, regarding the application of neural networks to parameter estimation, yes. I mean, mostly these techniques have been explored in order to speed up the process. There are also other intentions in order to be able to learn the model, so to train your neural network on your particular cosmological model, and in order to avoid running the model as well. So there are two aspects as well. One can see that, because you can develop your neural network in order to literally mimic the MCMC technique. So instead of running MCMC, you run neural network, and you speed up the process. Another way of seeing this is to train your neural network in order to understand better the cosmological model. So instead of running, for example, class several times in an MCMC, you will call the trained model via a neural network, and then that will be much faster as well, because you will not be calling class all the time.
Thank you, but I guess I have a follow-up question. Aren't these things that you mentioned more connected to the computational performance, which I'm not saying is definitely, I mean, it's definitely something to consider, but I was wondering in terms of benefits to a more accurate parameter inference or coming up with a cosmological model, if there were any significant differences between the two.
Yeah, that is something which is also still being explored. As I've mentioned briefly, neural networks have also been used in the reconstruction or realization of simple functions, so like the distance modulus, for instance, from supernovae. We have seen, at least in the community, that in general, when one considers the neural network techniques with respect to other techniques, so let's say we compare Gaussian processes with neural network reconstruction techniques, what we have seen is that the error bars that you get, so the uncertainties that you get, are more realistic in a sense that they are not tightly constrained when we consider the same data set. And this is quite important, because in the case of a Gaussian process, normally the uncertainty is quite tight. And when we apply the same, when we adapt the same data set to a neural network technique, what will happen is that the uncertainty increases. And it will definitely be more realistic, especially when you test it with different testing data sets. You will get into more agreement with the neural network technique with respect to the Gaussian process technique. In the case of the MCMC versus the ANN technique, in order to infer model parameter constraints, in that case, we have also noticed that the parameter constraints that we get, so that is the contours in the triangle plot, they are more conservative with respect to the MCMC. So somehow the MCMC technique is being shown to over-constrain a bit the contours that we're getting on the model parameters. So there are two different techniques. They mimic each other. However, we are getting slightly more conservative constraints in the neural network perspective.
Okay, thank you very much.
Yeah, the comments, queries, curiosities? If not, then Jürgen, maybe you could describe a bit the exercises.
Yes, yeah, I mean, I would like to show you what happens in the Pantheon Plus dataset, because this is quite different to the JLA dataset, which I have shown earlier in the lecture. So in the case of Pantheon Plus, first of all, here you have the link from which you can get the data sets. So in this case, you need the actual data. So that is the mean values, and also the covariance matrix. Okay, because in a Gaussian process, we can also consider the covariance matrix of our data set, and it will be taken into consideration in the calculation of the realization of your reconstruction. Okay, so that is important to mention as well. So in the case of the data sets that we're going to consider, they look like this, basically, when you download them. Maybe some of you are familiar with this data set already. So we're going to use only a few columns here. So we're going to use the squared errors. The squared errors are coming from the diagonal part. And this is basically what we'll be considering as a data frame. So as a data frame, we will have the redshift, we'll have the distance modulus, and also the errors. Okay, so that is what we're going to consider. If we were to plot the data points of the Pantheon Plus, so mu of z versus z, these are all the data points that we get. I'm not applying any cuts here, any redshift cuts. And if we go through the same process, so let's say with a particular kernel, okay, one of the kernels that we have already used within GPyTorch. So we apply the Gaussian process on our data sets, and so on the raw data set itself. So that is the data point as a function of redshift. We're going to use the Gaussian likelihood, and we're going through the training part. Optimizer is the same, the ADAM, and the loss function is the exact marginal log likelihood. Again, we're going to consider 200 iterations, and we process the model. Okay, so after the training, you will end up with this reconstruction. Okay, so as you can see, the realization that you get is not the expected realization at all, right? Because, as I've said in the beginning, a Gaussian process realization is able to also impute your realization. That is basically when we have a gap in data. So, for example, here or here, where we don't have any data points, a Gaussian process realization is expected to give us a continuous realization and an imputation technique as well. We can also carry out some forecasts from our realization. So the issue here is not about a failure of the technique, okay? But what is happening is that we have to think about how we can make the smoothing technique of Gaussian processes work, okay? And one way in doing this is by considering different scaling of the x-axis. Okay, so over here we are considering linear redshift, okay, from 0 up to 2.5. If we were to scale the x-axis, so that is the redshift phase, logarithmically, okay, so all I did over here was that I took the same y values, the same errors, okay, so the same uncertainty of each data point. But in the case of the x-axis, I have considered a logarithmic redshift scale, okay, not a linear scale, as you can see over here. In that case, so I left everything the same. So basically, Gaussian likelihood, ADAM optimizer, exact marginal log likelihood. Number of iterations is the same, 200. And the result would be the smoothed reconstruction of the distance modulus. Okay, so as you can see, the reconstruction now is smooth. It obviously the majority, it fits the majority of the points over here, okay? And then you have some points over here which are not exactly in line. And this is precisely what I was saying regarding the overestimation of the errors, okay? Because as you can see, since you have a lot of data points here with very small error bars, you end up with a very small uncertainty in your Gaussian process realization. And this then goes on as a function of redshift. Okay, when it comes to a neural network, that part will be slightly more conservative. That is, the uncertainty will be more realistic. Okay, in order to consider all the data. Now, you might say, okay, this might be an effect of the kernel. So if I were to change the kernel, I would be able to have a proper realization. However, here, again, I will change the kernel to an RBF kernel. I carry out the same process, okay, so same training and so on. And as you can see, this is the fit. So the realization of a Gaussian process, even with another kernel, but with linear redshift, you cannot get a proper realization from your Gaussian processes technique. So again, if we apply a logarithmic in Z, so logarithmic in X, in this case, again, we get the actual, or let's say the expected results of our realization. Okay, so this is something which should be noted. That is, sometimes the reconstruction techniques might seem to fail in certain data sets. However, it's not exactly the case, because then you have to think about how the procedure works. Okay, so what you are inputting and how the input is being interpreted in the realization itself. Basically, a Gaussian process, you remember from lecture itself, I've mentioned that one of the hyperparameters is related to a length scale. If the length scale changes, okay, along the x-axis, so the length scale, basically, let's say, consider the length scale as our separation of data points. The separation of data points here up to redshift 1 is very small, but over here, the length scale increases. Okay, so you have two different values of the separation, let's say, of the mean separation between the data points, and therefore, one of the hyperparameters is affected. And the problem is that we only have one hyperparameter which is going to be fixed for the whole realization. And therefore, in that case, we will not be able to fit. In fact, as you can see from the previous reconstruction, over here, we are able to fit it because you've got a particular length scale, but then over here, you are not able to fit it because you have a different length scale. Okay, so these things are, let's say, quite important to consider, especially when it comes to adapting the same technique to different data sets. And this is similar to what I was saying in the case of mimicking MCMC with respect to ANN. In the other notebook, there is this exercise in order to infer a decision boundary, in this case, with respect to declination. Okay, so in this case, the data set is as follows. So it's a redshift declination plot, and we would like to find a linear boundary. So that is, we will be able to separate our manifold with a hyperplane. In this case, in the redshift declination space. Again, in this case, we're going to use the perceptron with a learning rate of 0.8 and 1,000 epochs, so it's quite a bit of epochs. And this is the output that we get. Okay, so again, the perceptron technique was enough for this data set in order to find to to separate the two data sets. Okay, so I will be uploading these two notebooks on the GitHub page. It will be called the training series CosmoVerse. You can find the notebooks there along with the figures and so on. And if you have any questions or you are interested in this subject, I would be more than happy to answer any questions after the lecture. I should also mention, I'm pretty sure that this has been mentioned in the other lectures as well, that this part of machine learning and similar techniques will also feature in the white paper of this course section. So that is something which you should also keep an eye out. Okay, so with that, I can close. That's all from my end.
Thanks again, Jürgen. So, and to everybody for making the time to be here today.